Hi guys, welcome to my first Calculus 2 video. So I decided I'm not going to be filming the normal classes, but instead what I'm going to be doing is I'm going to be uploading videos to kind of augment the class. I'm going to be uploading videos that touch on certain topics I feel like my students might need a little bit more practice with. So whether you're my student or not, I hope this video helps you. So I am teaching Calculus 2, and one of the main ideas of Calc 2 is strengthening your skills with integration. We learn how to use all of these different integration techniques to integrate all of these different functions. We learn how to recognize certain types of functions, and we learn about different ways to simplify things algebraically before we integrate them to make things easier. And we learn techniques to do the integrals themselves. So in this particular video, I'm going to be covering a technique called integration by substitution. It's otherwise known as U substitution. That's a pretty common name for it, U substitution. One of many names for it. So the thing about U substitution is when you're learning this for the first time, you may not be exactly clear on when and why you have to use it, in which situations you have to use it. So we can think of this as being the reverse of the chain rule for derivatives. Every integration technique is the reverse of some derivative technique. So for example, if we have some function, let's say we have f of x. The handwriting is really horrible tonight. So let's say we have f of x is, let's make it an interesting one. Let's say we have 2 times sine of x cubed, and we're interested in finding f prime of x. So we know we're going to have to use the chain rule for this one. How do we know? We know because we have a clear outer function, or we have a clear inner function right here, and we have a clear outer function right there. So that's a dead giveaway that we have to use the chain rule. So we're going to use the chain rule in conjunction with the power rule. We're going to multiply 3 by the constant that's already out there. 2 times 3 gets us 6. And then with the chain rule, we're going to leave the inner function alone for now. It's still going to be sine of x. But then we're going to use that power rule for derivatives. We're going to take 1 away from the exponent, make it 6 times sine of x to the second power. And then the chain rule tells us we have to multiply by whatever happens to be on the inside of the function. We have to multiply by the derivative of the inner function. So our inner function is sine of x. The derivative of our inner function is going to be cosine of x. So that's the chain rule for derivatives. It's just a nice review, a refresher in case you don't remember how the chain rule works. That's how it works. But what happens if we're given this and we're being asked to integrate this? Easier said than done, right? We know what the syntax looks like to integrate something like this. And sorry if I'm going back and forth between different notations. My OCD is kind of going off the charts right now, so I'm sorry if yours is too. I apologize in advance for that. So how do we integrate something like this? So we're going to use the same kind of approach that we use for the chain rule. So with the chain rule, we identify an inner function, and then we take the derivative of that inner function and put it somewhere in the expression. We multiply the entire expression by the derivative of the inner function. So now we're going backwards. We have one function, and we have the derivative of that function somewhere in the integral. So I'm going to go back on my word. I'm actually going to go back to that old notation convention. I'm going to make it like this instead. You guys will see why in a second. You'll see why this is the preferred notation when you're doing a problem like this. So we want to decide what would be an inner function, and then we want to decide if we have the derivative of that inner function somewhere present in the integral. So the u part of u substitution is going to be a function. We always want to assign a function to be u, because ideally we're trying to go backwards. We're trying to get from this step back up to this step. So we always have to identify a function to be u if that's our goal. So u should be the function that not only looks kind of like an inner function, but looks like the derivative of that function is somewhere in the expression. So we have a clear inner and a clear outer function situation. We can see that this 2 would be a really nice outer function. This sine of x would be a really nice inner function. So we can tell for sure that this is going to be a really good candidate for u because it's an inner function. It has to be an inner function for this to work properly. That's one condition. The other condition we have to follow if we want to use u sub is we have to have the derivative of that inner function somewhere in the integral. So let's verify that. Let's see if we have that. So theoretically, if we set u to be the sine of x, we want to take the derivative of that and then see if that's present somewhere in the integral, because if it is, we did a good job. We can pat ourselves on the back. That is a mighty fine, that's a mighty fine function to use for u. It's a good thing to assign to be u. So the derivative of sine of x is, of course, cosine of x. And hey, look, we have that. So remember the two conditions for U substitution is, if you're trying to decide whether U substitution can work in an integral problem like this one, you have to make sure that the two conditions are met. The first condition being that we have a clear outer function and an inner function situation, which we do. So it looks like this would be a clear inner function, and then this 2 right here, the second power, would be a clear outer function. So that's the first condition that's been met. The second condition is we have to have the derivative of this inner function somewhere in the integral. And well, look, we do. We do have that. We do have the derivative of the inner function. We've satisfied both of the requirements to do an integral using U substitution. So we are clear to continue. So right here, we have what's called a differential equation. A differential equation is just an equation that involves some kind of a derivative. So this du dx, derivative of u with respect to x, this is a derivative. Our equation contains a derivative, so this is a differential equation. I'm going to modify this differential equation to make it look a bit more like what we have. So I'm going to explain exactly what I mean. So we have u squared right here. This entire thing in the box right here is u squared. But then what about all of this stuff? We want to make sure we have substitutions for the rest of that as well. So notice how we have a substitution for the cosine of x, but we don't have a substitution for the dx. We don't have a complete match just yet. So what I'm going to do is I'm going to modify this differential equation. I'm going to multiply both sides by dx. And then when we do that, we get this as our final result. We get du is equal to the cosine of x times dx. And notice how it's a perfect match. So we have a substitution taking up everything. So that's what we have to do in a U substitution problem. Something else you need to check after you pick a U and you have to pick a DU is you always really need to verify that you have everything taken up in a substitution. So if we had only this part DU, it wouldn't work because we have this DX going unaccounted for. But if we have this entire thing be DU, then we're good to go. So we can't have multiple variables. We need to have either everything in terms of just x or everything in terms of just u. It wouldn't work to have just this be du, because if we replace cosine of x with du, we still have something involving x, and we can't have that. We can't have two different variables. We can only have everything in terms of x or everything in terms of u. We can't have a mix of variables in the integral. So that's the whole reason why we modified this differential equation. That's why we moved this differential right here, dx, to the other side. We just can't really have a mix of variables, and this does the job quite nicely. So now we're at the substitution part of U substitution. We're going to make this 6 times, this is going to turn into just u squared. And then everything else is going to turn it into just du. So it's already looking much, much easier. So pretend this were an x. If this were x squared dx, we know how to integrate that, which means we also know how to integrate u squared. So it's a different letter, but the math works exactly the same. We're going to use that same integration power rule to integrate u squared. So the 6 is going to remain. We're going to add 1 to the exponent. So it was a 2 before, now it's a 3. And now we're going to divide by that exponent. We get 3, 1/3. And then we're almost there. The only thing we need to do now is to put u back in there. And then simplify a little bit. So this is going to be 6 times 1/3. That gets us 2. We're going to get 2 times u cubed. So that's going to be 2 times sine cubed of x plus c. And hey, we get exactly what we started with, so we know we did this correctly. That's U substitution in a nutshell. Let's practice a few more problems. Let's say we have 4x to the 3rd power times cosine of x to the fourth plus 2 dx. And we're trying to figure out if this is a U substitution problem. We're trying to figure out if we have to use U sub in this situation. And the way we accomplish that is by making sure we meet both of those conditions I mentioned earlier. We have to make sure that not only do we have a clear inner and an outer function situation, but we have to make sure that whatever function we choose to be the inner function, we have that derivative somewhere in the integral. So it's pretty easy to see that in this part alone, we have something on the outside, which would be the cosine function, and we have something on the inside, which would be x to the fourth plus 2. So that just tells us right away that the x to the fourth plus 2 would be a really, really good candidate for U. So what I'm going to do is I'm going to set U equal to x to the fourth plus 2. And then I'm still not completely convinced we can do U sub here. I still have to take the derivative to verify that the derivative of the inner function is present somewhere in the integral. So if we take the derivative with respect to x of x to the fourth plus 2, we're going to get 4x cubed plus 0. And then I'm going to do what I did before. I'm going to modify the differential equation just so it also takes up this dx. We have to make sure it takes up both of these things. Can't just take up the 4x cubed. It has to take up the dx too. Otherwise, we can't continue the substitution. So it's going to be du is going to be 4x to the third times dx. I'm sorry if I sound congested. Allergies are killing me right now. And it's pretty brutal. So if I randomly go off the screen, it's because I'm having a really bad allergy attack. I almost think it would be more merciful to just kill me and put me out of my misery because this is brutal. It's been going on for a long time. I was supposed to move to Reno, but that's actually being pushed back to August because the place I really want to move into won't be available until then. And I'm just really looking forward to going back. I've considered Reno to be my true home, and I hardly ever get allergies up there. So it's enough about my fantastic, exciting life. Let's get back to math. So we have du in terms of x. And this is perfect. The reason why this is perfect is, well, I'll show you. I'm going to rearrange this integral. And remember that multiplication is commutative. That means we can multiply things together in any order, and it does not change the answer. So me doing the old switcheroo on this thing right there and this thing right there, I just switched those. But it has no effect on the answer because multiplication is commutative. We're still going to get the same answer no matter what order they're in. So the reason why I'm doing that, though, is because it's a little bit easier to see why we're choosing the substitutions we chose. So this right here, this is going to be cosine of u. And then this part right here, well, look, that looks pretty familiar. That looks like exactly what we have for du. So this entire thing right here can be replaced simply with du. So let's go ahead and do the substitution part of U substitution. Cosine of u du, we're faced with a much easier problem now. So the antiderivative of cosine, of course, is going to be sine, which means this is going to turn into sine of u plus c. That is our particular solution. And u happens to be x to the fourth plus 2. All right, so we have our answer. Let's keep practicing. So I invite you to pause the video and try this one on your own. I want to just say right away that yes, you can do U sub. I don't want you to take too much time wondering if you can or cannot. I just want to give it away right now that yes, you can do U sub on this one. So pause the video, give it a try. See if you can pick the right values for u and du, and see if you can carry it out to the end. All right, so we have a clear inner function and we have a clear outer function. So we can clearly see that this radical would be a good candidate for the outer function. And then everything inside this radical would naturally be the inner function. So u is always going to be the thing we assign to be the inner function. So u is going to be 2x plus 1. That's the entire thing we have under our radical. And then the derivative of our inner function, our derivative of u is going to be just 2. And then we're going to modify the differential equation. But hang on a second. Notice how we don't have a 2 anywhere in the integral. It would be really, really nice if we had a 2 right there, because if we had a 2 right there, let me just show you. So I'm going to move the dx to the other side in the differential equation. If we had a 2 right there, it would work out really, really nicely because together, the 2 and the dx make up du. So we could just replace them together collectively with just du. But unfortunately, we don't have that 2 there to help us. So we're going to have to think about another way to approach this. So how do we account for the fact that we have a 2 right here, but not in the integral, not outside of the radical? I mean, we have a 2 right there, obviously, but we really need to have one outside of the radical, and we don't. How do we account for that fact? I am so glad you asked. So I'm going to modify this differential equation the way we're used to. I'm going to multiply both sides by dx. So then we get du is going to be 2 times dx. And then from there, I'm going to divide both sides by 2. And the reason why I'm dividing both sides by 2 is because we have a dx, but we don't have a 2dx. Our goal is to make this look exactly what we have outside of the outer function. So the only thing we have outside of the outer function is dx. So we want to isolate whatever we have. We want to isolate dx. And in order to isolate dx in this situation right here, multiply both sides by dx, divide both sides by 2. So that's how we isolate dx. We get the following. We get dx is equal to du over 2. So let's go ahead and do the substitution now. So we're going to integrate from 0 to 4. This is a definite integral problem. Our answer is going to be a number and not a function. So we know that everything under the radical, we assign that all to be u. We just called all of that u. So this is going to be square root of u. And then notice how we have a substitution for dx as well. So instead of dx, I'm going to write du over 2 because we know dx is equal to du over 2. So I'm going to just rewrite this as du over 2. So let's do a few things that would make this a little more intuitive, easier to integrate. So we're going to integrate 0 to 4. So we can move this constant multiplier outside of the integral. So this is like saying we have 1/2 times du. Let's go ahead and move the 1/2 out front. And then what we can do is we can make this square root of u into u to the 1/2 power times du. All right, and then from there what we can do is we can take the antiderivative the same way we're used to doing it. So we have u to the 1/2, just a single variable to a power is really easy to integrate. So we're going to add 1 to the exponent. So if we add 1 to 1/2, we get 3/2. So this is going to be u to the 3/2 power. And then we're going to divide by that result. We're going to divide by 3/2. So dividing by 3/2 is the same thing as multiplying by the reciprocal. Dividing by 3/2 is the same thing as multiplying by 2/3. So that's where that part comes from. We're going from 0 to 4. So we can simplify a little bit. So we have 2 times 1/2 is 1. So the 2 and the 1/2 cancel each other out. We're left with this. We're left with 1/3 u to the 3/2, which is going to be 2x plus 1 to the 3/2. I'm going to clear up some space. Whoa, didn't mean to do that. I hope at least you get some entertainment value out of this. Watching me fail with Zoom, hope at least it brought a smile to your face, if nothing else. So we have our function, our antiderivative. We're evaluating it at 0 and 4. So we have 1/3. This is going to be 2 times x. 2 times 4 gets us 8. Plus 1, 9. So we're going to have 9 to the 3/2 power. And then it's that second fundamental theorem of calculus that tells us we always have to plug in our top endpoint into the function and then subtract whatever we get when we plug in the bottom endpoint into the function. So our bottom endpoint is 0. If we plug in a 0 for x, we're going to get 0 plus 1. So we're going to get just 1 to the 3/2. So 9 to the 3/2. So let's ignore the 3 for now. 9 to the 1/2 power is 3. And then 3 to the 3rd power is 27. So this is going to be 27 minus 1 to the 3/2. That's going to be 27 minus 1, which is 26. So we get 26 times 1/3. We get 26 thirds as our final answer. Let's try some more examples. Let's say we have pi times the integral going from 1/6 to, let's make this, I don't know, let's maybe make this, what do I want to do here? I haven't decided. Maybe 2/3. Yeah, 1/6 to 2/3. And we're trying to, the function we're trying to integrate would be cotangent of pi times x dx. So this one's a bit of a doozy. It may not be clear exactly what we want to do here. It may not even be clear that it's a U sub problem, but it definitely is. So we want to rewrite this in such a way that we're able to actually do U sub, because right now it doesn't look like we can. So we're going to use those trig identities. I'm going to write this as the reciprocal, no, sorry, I'm going to rewrite this as cosine of pi x divided by sine of pi x. That's what cotangent is equal to. Cotangent is cosine over sine. So I'm going to be really lazy. I'm going to just replace this with cosine over sine. And then from there, it looks like we can make u be whatever we have on the bottom. So let's talk about that real quick. Do we want the sine to be u, or do we want the cosine to be u? Well, if cosine is u, that means sine would be du, which means we would have u over du, and we can't have that. We can never have du downstairs in the fraction. We can only have du go upstairs. So whenever you're deciding in a rational function like this, what should be u and what should be du, always have u be what's on the bottom. Always have du be what's on top. You can never have du downstairs. You can only have du upstairs. So that means whatever we have downstairs, in this case it's sine pi x, that's going to be RU. And then we're going to do the U substitution. We're going to take the derivative, and then I'm already going to multiply both sides of this by dx. So this is going to be pi times cosine of pi x. We're going to use that chain rule to take the derivative of u. There we go, nice and easy. So I noticed that we have the cosine pi x and the dx, and we also have the pi there too. So for this particular example, whoa, I didn't mean to move the c out of the way. The only thing I meant to do is move the pi to the inside. And the reason why does this keep happening to me? I think the computer's laughing at my pain. So the reason why I put pi on the inside is just to make it super clear what's going to happen next. So on top, upstairs, we have pi cosine of pi x times dx. And look, that's exactly what we have here, verbatim, in the same order and everything. So that tells us we can take this entire thing and just replace all of that simply with du. So that's why I moved the pi to the inside, just to make it clear that it's part of du. We have to include the pi in our definition of du, otherwise it won't work properly. So I'm going to replace everything in this box with du. So our new expression we have upstairs is going to be du. Our new expression we have downstairs is going to be u. So now what we can do is we can take the natural log of this, because we know whenever we have 1 over x, the antiderivative of 1 over x is natural log of x. So naturally the antiderivative of 1 over u is natural log of u. Natural log of sine pi x going from 1/6 to 2/3. And sorry, I might have skipped something there. So maybe we'll just call this u for now. I didn't mean to skip that step. So let's make this a natural log of u. And then we're going to replace u with sine of pi x because that's what we set it equal to initially. That's our value for u. So let's go ahead and evaluate this thing. So we're going to do that second fundamental theorem of calculus that tells us that whenever we have a definite integral situation like this, we're going to plug in our top endpoint for x. So we're going to get natural log of sine of pi times x. That's going to turn into sine of pi times 2/3. And then the fundamental theorem of calculus, the second part, tells us that we're going to do the same thing, except that we're going to subtract this time, and we're going to plug in our low endpoint for x. We're going to plug in 1/6 this time for x. So it's going to be natural log of sine of pi times x, or natural log of sine of pi times 1/6. All right, so let's simplify. So this is going to be 2 pi over 3. And remember, when we're trying to figure out these trig values, we want to visualize the unit circle. So this is going to be 2 pi over 3. So if a semicircle is one multiple of pi, if going all the way here is pi, then that means 2 pi over 3 is going to be right here. So this is going to be a 30, 60, 90 triangle. So the sine of this is going to be √3 over 2. So sine of 2 pi over 3 is just going to be √3 over 2. And then we have pi times 1/6 for the second part of our expression, for the other term. So pi over 6 is going to be 1/6 of the full circle, which is going to be right there. And the sine of pi over 6 is 1/2. So this is going to turn into minus natural log of sine of pi over 6, or just natural log of 1/2. And if you wanted to simplify this, you definitely could, but it's not completely necessary. The main goal of this video is not to review trig so much. It's just to review integration by substitution and make sure we have the calculus part of this down. This is a calculus class. Our main goal is to practice calculus operations. So like I said, you could simplify this, but if you turn this into me as a homework answer, you would get full credit for that. This is perfectly acceptable. On a good day, if I have my coffee, I would accept this. But if I'm in a bad mood, if I haven't had my coffee, watch out. I'd probably make you simplify it further. I'd probably be mean about it. But as it stands now, this is perfectly fine. All right, I think we might want to do, I think I want us to do maybe just one more. I thought this was an interesting one. But Justin, I thought you said you can't integrate things that have multiple variables. I see A, I see B, I see C, and I see X. Well, you're on the right track, but this thing actually doesn't include multiple variables. I know it kind of looks like it does, but X is the only variable we have here. So A, B, and C, they're not variables, they're constants. We don't know what they are. We don't care about what they are. It does not affect the way we integrate this. The calculus part of this is going to work exactly the same, whether this is an AX plus B or if it's a 2x plus 1 or a 4x plus 3. It doesn't really matter. We're going to treat A and B just like we would any old number. So this is a U sub problem. We have a clear outer function. We have a clear inner function. Let's just make sure we have the derivative of the inner function somewhere in the integral. So whatever happens to be under the radical is a really good candidate for the inner function. We're going to have that be U. U is going to be ax squared plus 2bx plus c. So I'm going to take the derivative of that, and then I'm going to move the dx to the other side, isolate du, and I get the following. I get 2ax plus b dx. Sorry, plus 2b dx. to be or not to be. All right, so we have something really, really close to what we have. Upstairs, we have ax plus b dx, but unfortunately, we don't have those two coefficients there. We don't have a coefficient of 2 for the ax or for the b. So we're going to need to be clever in how we deal with this. We're going to need to divide both sides of the differential equation by 2, which means we get 1/2 times du is equal to just ax plus b dx. So we have 1/2 integral du. So 1/2 du is the equivalent of all of this. So we're just replacing all of this with 1/2 du. And then on the bottom, we have square root of u. So that's going to be just, I guess, u to the 1, I'm going to just write it like that for now. So now let's simplify it a little bit, make it easier to integrate, make it a little more clear about what we have to do. So instead of du over square root of u, I'm going to write this as u to the negative 1/2 times du. So it should be a little more clear about what we have to do now that it's in this form. We're going to add 1 to the exponent, we get 1/2. So it's going to be u to the 1/2. And then we're going to divide by that result. We're going to divide by 1/2, which is the same thing as multiplying by 2 over 1, the reciprocal. We do have to have that plus c. So then the 2 and the 1 are going to, the 2 and the 1/2 are going to cancel each other out. We're left with just u to the 1/2, but instead of 1/2 exponent, I'm going to rewrite this. I'm going to make this u to the 1, I'm going to make it square root of u plus c. And then u happens to be that thing we set it equal to at the very beginning. And I'm kind of anxious about having 2 different c's. They're supposed to be different values, so I'm going to be fancy. I'm going to make the limit of the constant of integration a k. So whenever c is being used, it's natural just to have k be your constant of integration. So this would be our complete solution. All right. Hope you learned a lot from this video, and I'll see you guys next time.